today we are going to focus on electric current. Okay. Now, we already saw that if there is a point here and this point is at a potential of, let us say, 12 volts and some other point which is at a potential of 6 volts. Now, this may not be lower, I have just drawn it lower, it could be higher, lower, because physically it doesn't matter. If it was 12 volts and 6 volts, right now if I had a positive charge, the positive charge would like to go there because it likes to lose its potential energy. So, a positive charge, if I could connect these two by a wire, then positive charges would tend to move this way. Of course, in reality positive charges don't move because they are actually stuck to the atom. So, unless you have a ionic solution. So, if you have a solution, for example, if you had sodium chloride in a solution, basically you mix up salt water, then sodium ions and chlorine, basically chloride ions, both can move because they are in water, so both can move. It's very slow process, but you can have positive charges moving. It's not that it's impossible, but most situations, like if I had a wire like all of this situation here, if you take AC, any of these wires, it's really not the positive charges that are moving, but it is the same as positive charges going this way would be the same as negative charges going that way. Okay, because there are so many charges that are available that if I had this thing which was neutral, 20 plus and 20 minus, actually it will be more like 20,000 plus and 20,000 minus, actually more like 20 trillion plus and 20 trillion minus, because you are talking about trillion is 10 power 24, 1 mole is about 10 power 23. Now imagine that I took out 10 of the plus. What do I have here? I have 10 plus and 20 minus, which is equivalent to, right now it was 0. Instead later what has happened once I have taken out 10 plus? It has become 10 minus. Suppose I had put in 10 minus instead of doing this. Suppose we started with 20 plus, 20 minus and I put in 10 minus. So it will totally be, the beginning it was 0, now you have 20 plus and 30 minus, and so that overall is going to be 10 minus. Whether I did this or I did this, it is still 10 minus. So we claim that 10 plus moving that way leaves a net charge of 10 minus. 10 minus coming in obviously will leave a net charge of 10 minus. So 10 minus moving this way is equal to 10 plus moving that way, because overall the system was initially neutral. So what matters is not how much actual plus you have and actual minus you have, but actually what matters is the difference, that is excess charge that you have. So if you have excess of 10 minus, that's basically what counts. This is going to happen this way, it's going to be 20 plus 30 minus. This is going to happen 10 plus 20 minus, but we don't care that this is 10 plus and 20 minus, 20 plus 30 minus. That difference we don't care about. We care about the fact that overall it is 10 minus and overall this is 10 minus. Okay. So we only care about the fact that the net excess charge is either plus or minus. If it was plus, we claim a total of plus came in. Actually, instead of plus coming in, it could have been minus going out, which is more likely of the situation that happens. So anyway, you know that if you had 12 and 6, this plus would like to go there or this minus would like to go there, because minus likes to go from lower potential to higher potential. Now either of these situations creates what we call a current, basically flow of charges. Now each charge will carry energy. So we usually have, you are quite used to circuits, right? So if you take a situation like this, you have some charges that go this way, go into this bulb and come out of the bulb. Generally what happens is whatever current goes in or whatever charges go in, they'll all come out. Not necessarily the exact same charges, but equivalent charges. So think of one marble coming and hitting and another marble going this way. But effectively, one marble came in, one marble went out. So how many extra marbles came inside? Actually none. Well, what came in went out. If all the electrons basically get out, electrons would probably move this way, plus charge move that way, doesn't matter. So right now let's assume that there are some charges that are going this way, they go and then they come out. None of the charges were used up. How come this bulb radiates out light? Where is it getting its energy from? Because it's really not using up any of the charges. Movement of charges, why should it cause light? So what has actually been used, you didn't use up the number of charges. You had, so are we saying that I sent in 3 charges, only 2 came out? One got eaten up and became light? No, right? So that's not what electricity does. So in flow of electric current, if you had 3 going in, ultimately 3 come out. Because you can't just suddenly get the charge getting destroyed. So the charge is not destroyed. So whatever comes in goes out finally. So then what is this? How do you get the so what do
rate is slower coming out, so it stays there for a longer time.
So you are saying first I sent 4 into this wire and then I have a bulb here, whatever is happening here, okay, and then in the beginning 2 come out. So for a while I take out the other 2 and then make them into light and send them off. And then what do? I catch hold of the light that bounces off and then convert it back to these electrons or protons and send it out. Is that what I'm doing? No, right? So, well, if you are going to have 2 coming out, the other 2 are parked there doing what? Doing nothing. You can't destroy them. If you destroy them, you don't know how to create them in the first place. So, since we can't create or destroy, all 4 come out. And actually what we are going to study today is the fact that if 4 of them go here every second, 4 will go out every second. It's not even like it goes in, waits for half an hour and then comes out. It goes in and comes out right now. Right now, as it's going in, it's coming out. So then what is actually getting used up? The energy of these guys. Okay, so you will see that what really gets used up is that these fellows have more energy sitting there. They have less energy when they are there. By the way, this is very common. We use it all the time. So how much water do we use up? Just imagine that question. We answer that question many times, right? So how much water did you use up today? Don't use up too much water to take a bath. Correct? Now, did you actually use up water? You took a mug and you poured water on yourself, and that water basically stayed inside you. It goes and sticks inside. So when you come out of the bathroom, you are carrying blobs of water on your skin. Is that what you are doing? So how much water do you actually use up, that is take with you when you take a bath? Unless you kind of drank a little bit of that water, hopefully you didn't. What happened to all the water that you poured on your head? Just went down. So what water did you use up? You never used up any water because all the water went down. So what do we mean when we say use up water? Hopefully we got some nice clean water and then we sent out dirty water. Okay, same amount of water. We messed up that water. So when we say use up water, what we mean is mess up water. That's what we actually mean. So if you think about what this bulb has done, is not really use up charge or use up current. What it has done is to mess up the energy of the charges. It has taken away something which was at a higher level of energy and produced something at a lower level of energy.
If first all the charges have certain amount of energy, the bulb uses up some energy, no sir, then shouldn't it take more time to come out? Because you said it will come immediately.
Correct. So you are assuming that the energy is in the form of speed or kinetic energy. But that's why we talk about potential energy. Okay. So I have right now a tub at a higher potential energy, water comes out, right? Now let us say water enters this tub. Now this thing is at lower potential energy. Now the amount of water that comes out at any time is equal to the amount of water that goes here at any time, right? So this is at a higher potential energy, this is at a lower potential energy, which is why it wants to come from there to here, because it wants to reduce its potential energy. But if you think in terms of how much came out, if for example a lot of water comes out and very little water comes here, where does that extra go for some time? So this pipe will become a little fatter. Is this what is going to happen? So are you going to have like fat pipe, after some time it will flow out? Is this what will happen? Well, if it was empty pipe in the beginning, yes, water is going to take some time. But once you connected it, whatever enters here must get out, because there is no more space on this pipe. It's full. But this pipe has higher energy water coming in and lower energy water going out. So what happened to the remaining energy? That's exactly what it lost. Okay, lost means it lost. Somebody else must have gained it. There is friction, there is a lot of other things which will basically take away that energy, right? Now the energy of this charge, energy of that charge, if you compare, this charge will be at a higher energy, that will be at a lower energy. If you put negative charges, which is why let's say this was 12 volts and that is 6 volts, the energy is the number of charges, the amount of each charge into the potential. Remember, it is Q times potential. That is the energy, right? Remember that? We did this. Q into V would be U, potential energy. V is potential, but if you have a charge, the charge into the potential gives you the potential energy. So the amount of potential energy will be the amount of charge into 12 volts. Whereas here, it will be the same amount of charge into 6 volts. Now, if the charge that goes through, if you wait for 2 hours, then lot of charge will go through. A lot of charge will go from 12 volts to 6 volts. So obviously you will get lot of energy. But if I want to look at power, that is amount of energy that is coming out of this every second, what should I look at? How much charge goes from here every second? Because that much charge would go from here every second. Do you understand? So we are therefore interested in knowing how much charge passes some particular point or an area every second, because that tells us what we call current, because this much charge each second, let's say this was I, we call this I, current. Now this tells you that 4 units of charge, 4 coulombs of charge pass every second. How much energy did they come with? 4 into 12, 48 joules of energy every second. But then when they come out, it's not like they have 0. Because if 4 units of charge go this way, 4 units will hopefully go that way in the same second. But that 4 unit will have how much energy? 4 into 6. So that will have 24. This guy came with 48 joules, went out with 24, which means how much did you give to the bulb? You only gave 24, because 48 minus 24. See, if you say I had a lot of energy and then I carry all my energy with me, how much did I give you? 0, right? So what I give you will depend on how much energy I lose. So if I start with 12 and this was 10 volts, I haven't lost very much. I have only lost 12 minus 10, which would be 2. Right now I have gone from 12 to 6, so therefore 6. Okay, if I had 12 to 8, 4. So can you see now why we learnt earlier potential drop? Because potential drop will tell you how much energy one charge actually is willing to lose. Because I had this much energy and that is lower energy. So that basically will tell us the 12 is not the energy, but 12 into charge will be the energy. But if I was 1 unit of charge, 1 into 12. 1 unit of charge, 1 into 8. But the amount of charge is not going to get vanished. So if I go this way from 12 to 8, it's the same amount of charge. So if I was 2 units of charge, I have energy of 24, and the same 2 units will come here with energy of 16. So how much energy did I supply? How much did I lose? 2 times 12, 24, 2 times 8, 16, 8. So that much energy I would have given this fellow. Now, do I do this over 1 second or 1 hour? Matters. If I say I will supply 2 joules of energy every second, in 1 minute I would have supplied 2 joules per second. So in 1 minute, 120 joules of energy. Okay, in an hour I would have supplied quite a lot. But suppose I say, no, I'll give you 2, but I'll give this to you over 1 year. So if your parents give you pocket money, and your father says, no problem, I'll give you 1000 rupees. But I'll give you this 1000 rupees every 2 days. So are you happy? Quite happy. They say, I'll give you 1000 rupees, but I'll give this to you every 2 years. Which means per week you hardly get any money, right? So it matters whether it was per year or per day. If your father said, I'll give you 1000 rupees per hour, obviously you are very, very happy, right? So now, therefore, the amount of charge passing through per second matters, because that will tell you how much energy will get supplied per second. We call this energy per second, what is the name for it? Power, right? So power is something that we are going to be definitely interested in, because without looking at how fast you are able to supply energy, many things that we usually take for granted will not work. So if you look at these lights, these are powerful lights, which means a lot of energy per second. If you have a very, very dull light, it will be less energy per second. Energy per second doesn't necessarily convert to amount of light, because it can also become heat. So then it's a wasteful light. With the same kind of light, if you take LED lights and LED lights, then you can compare. If you take an incandescent bulb, okay, and you take an LED light, for the same amount of energy, that fellow will produce a lot of heat, but very little light, which maybe we don't really care about, right? So anyway, so let us come back to the definition therefore of current, because we want to study flow of charges and the fact that when charges move from a higher potential to a lower potential, if it's negative charges, they will move from lower potential to higher potential. But basically they are moving from higher potential energy to lower potential energy. They are losing that energy. And hopefully we are using that energy in a way we want. So we are interested in the amount of energy lost every second. But that will basically mean that we are interested in amount of charge that is passing every second. Hopefully we already know how much energy per charge. And how much energy per charge will be called what? I am pointing to it. Come on, what will it be called? Potential. Okay, so you will know the potential here and you will know the potential there. That will tell you the amount of energy per unit charge. So if you know how much charge every second, therefore you will know how much energy every second. So therefore we define this quantity that we are going to call current.